Good evening. Please. I'm Moss Kaved, Dean of the College of Science and Engineering at the University of Minnesota. And I'd like to welcome you to the 13th annual Misel Family Lecture presented by the William I. Fine Theoretical Physics Institute, FTPI, at the University of Minnesota. We're greatly appreciative of the support by the Misel and Fine family, their support for the University of Minnesota and for theoretical physics. Thank you. I like us to recognize the family who are sitting here. Thank you very much for your support. FTPI is a tremendous asset to physics at the global scale, and certainly to the University of Minnesota and to the state of Minnesota. We take great pride in the accomplishments of the faculty and researchers in the Institute, and in fact, earlier this evening, we recognized a number of those through major awards from the physics and other national bodies in the scientific community. So I'd like to, again, take this opportunity to ask my colleagues from FTPI who are here and have been recently recognized at the national and international level to stand up and be recognized. And we're tremendously appreciative of the reception that these lectures get from the community. This is really amazing to have the community join us to enjoy the thrills of discovery, thrills of scientific discovery. We're very fortunate to have some of the leading scientists here to share that discovery with us, and we certainly hope that members of the younger members of the group in the audience would really take this into heart and be excited about that discovery and think about science and engineering as their future. And some of them hopefully join the College of Science and Engineering. So looking forward to that. I'd like to now introduce the director of the FTPI, FBTI, TPI, TPI, Theoretical Physics Institute is a lot easier. The Fine Theoretical Physics Institute, Professor Keith Olive, to introduce our distinguished speaker for the, thank you.
Thanks. Good evening and welcome to the Misel Lecture. This year's Misel Lecture, and I want to echo Moss's words that it's really gratifying to see so many people with an interest in physics and the kind of things that we do here in Minnesota. In introducing tonight's lecture, there's two words that I'll refer to. One is substance, the other is patience. What we're going to hear about is about waves. And waves are, if you think about it a little, waves are sort of funny things. I mean, many of us know a mathematical description of waves in terms of sines and cosines. But what are they really? The waves that we have most context with are water waves, probably. I think everybody since they're a kid knows about water waves. And if you think about what they really are, and you think, okay, it's the depth of the water going up and down in some sort of periodic way, and then traveling as well, propagating. But if it weren't for the water, what would a water wave be? It's a hard concept. It's a little bit abstract. And I'm sure you've heard, with a little pun intended, about sound waves. So what is a sound wave? Well, it's also some sort of fluctuation, in this case, in the density and pressure of a gas or a medium. It could be water as well. But what's a sound wave without the substance, without the medium? So is there sound in a vacuum? How about light waves? Light waves were a big mystery for a long time, is how they propagate, because what's the substance? Water waves need the water, the sound waves need the air or whatever the substance or medium is. So there was a proposal that there was something called luminiferous ether, and that had to fill up all of space, and that allowed light waves to propagate. That all got torn down when Einstein started developing relativity, and the mixture between relativity and electricity and magnetism made there no need for this ether anymore. It was also very, it also went against the rules of relativity, in the sense that relativity tells you there should be no preferred reference frames in the universe. Although that also seems not to be true, because there is a preferred reference frame, and that's from the microwave background radiation that fills all of space. We can talk about some sort of universal rest frame. Then the other kind of wave that we have, and that's the one that you're going to hear about tonight, is a gravitational wave. And for that to propagate, that actually goes back even farther, back to, I think, Newton's time, where again, some sort of ether was proposed to fill up the universe so that a gravitational wave can propagate. Now, patience, why do I say patience? And that's because sometimes in physics you have to be very patient, not just for me to get off the stage, but you have to be patient for results to occur. Couple of examples where a lot of patience were needed. One was the Higgs boson, and that was predicted in 1964 and then discovered in 2012, so nearly 50 years for that discovery to bear out the theoretical prediction. And if some of you were here, that we had a few years ago, one of the Misel lecture was designated for the discussion of the Higgs boson. But even more patience is required for what you're going to hear about tonight, because Einstein predicted the existence of gravitational waves back in 1916, and some indirect evidence for their existence was made in 1975, already a long time, by Hulse and Taylor, from looking at the motions of what's called a binary pulsar. But it wasn't until 2016, just a short time ago, that the LIGO collaboration, which is what we're going to hear about, made the first definitive discovery of a real gravitational wave. So let me introduce our speaker tonight, Nergis Mavalvala. She's the Curtis and Kathleen Marble Professor of Astrophysics at MIT. She did her undergraduate work at Wellesley, and she got her PhD in 1997 at MIT, working with Ray Weiss, who is a Nobel laureate from 2017. She did her postdoctoral work at Caltech and then came back to MIT in 2002 to join their faculty. She received a MacArthur Fellowship in 2010, and she was elected to the National Academy of Science in 2017. So let me introduce to you now Nergis Mavalvala.
So thank you. I don't think you should clap till you hear my story and then decide if it was worth clapping for. But thank you for the introduction. And thank you also, Keith, for introducing the idea of waves, because the journey that I'm going to take you on today is very, very bizarre. So you have to kind of hold on to your seats a little bit. So I'm going to talk about gravitational waves. It's in my title, so I must. But really what I want to tell you is this is a new window into the universe. This is a new way of looking out into the sky. Humans, as you know, have always been fascinated with what's out in the heavens for various reasons. And now, for the first time in this 21st century, we actually have a completely different way of looking at the sky than our own eyes and light. So I should do all of the most important things first. Everything that I'm going to tell you today, including the data that was taken by these instruments whose pictures I've shown here and I'll tell you more about was the work of a collaboration of over 1,000 scientists, of whom I'm one. So I put my name there just so you can blame me if you don't like the story, but the real people were the LIGO and Virgo collaborations, okay? So the story will begin actually with the announcement for the 2017 Nobel Prize in Physics, and I put this in quotes because this is what the Nobel Committee said. They said the 2017 Nobel Prize in Physics is awarded for a discovery that shook the world. Now, I really, I don't usually think of the Nobel Committee as witty, but this was very witty because it's both literally and figuratively true. Literally, because what you're going to learn is that that gravitational wave did shake the world, and figuratively because it also caused a lot of excitement. So who were the protagonists of this part of the story? Well, on the left is Ray Weiss, who is professor emeritus at MIT and my PhD advisor. And the other two were Barry Barish and Kip Thorne of Caltech. And these three were awarded this prize for decisive contributions to the LIGO detector and observation of gravitational waves. So it's a pretty big deal. Let me unpack the whole story for you a little bit more. So if I'm to tell you about opening a new window into the universe, I first have to tell you what the old window was. The old window was light. This is how we have observed the universe, and I'm going to give you one beautiful example. So here is an explosion. Now, this is not a movie of the explosion, it's an animation. What we're seeing is the remnant of an explosion that happened 300 years ago. This object is Cassiopeia A, and what happened here is that there was a star. About 300 years ago, there was a star quite similar to our own sun, and all stars, like our sun, will go through a life cycle. And the life cycle of the star is that it burns nuclear fuel. Actually, it turns out that the center of a star is a giant nuclear reactor, and as it burns nuclear fuel, it shines, and that the starlight pushing outwards keeps the star from collapsing under its own gravity. Have you ever wondered why stars don't just crunch together because of gravity? It's because all the light is pushing outwards. Now, like with any sensible system, it will eventually run out of its power source. It will use up all its nuclear fuel. And when that happens, the starlight shuts off, the star goes dark, and now it can't sustain itself against its own gravity, and it collapses inwards. It collapses inwards in an explosion where some of the material is ejected. And this is what you see. The ejecta are all the different colors of light are actually taken with 3 different wavelengths of light. So the reddish colors are infrared light, which is low energy emission. The greens and yellows are optical or visible light, which is essentially what our eyes can see. And then finally, the blues and purples are X-ray emission, which is the most energetic light. So you can see the most energetic light was for ejecta that blew out to the edges. Now, if you peer really, really carefully, at the very, very center, you will see a small little object. And can anyone tell me what color it is? Blue, yes. It's this teeny tiny little object in the center. And that actually is the star of this show. That object is a neutron star. It is the new star that was born when this parent star died. And it's called a neutron star because it's made up of neutrons, so you can think of it as a giant nucleus of an atom. It's not as giant as you would think, because this neutron star is actually only 10 kilometers in radius. Now, it has the mass of our sun, but it's 10 kilometers in size. So this is a pretty awesome object because our own sun has a radius of 700,000 kilometers. This thing is 10 kilometers big, but packs the same mass. So you can imagine it's pretty dense, okay? So that's the remnant in the life cycle of the star, and it's an important object because I'll come back to it in a little while. Now, if this parent star that exploded and left this neutron star remnant behind, if it had been a bit heavier, if it had been 3 or 4 times the mass of our sun rather than 1 times the mass of our sun, that star, that neutron star, would have continued to collapse under its own gravity, and it would have turned into a black hole. So lesson number 1, neutron stars and black holes are cousins, okay? Now, What do we know about black holes? Well, here is a picture of a black hole. This particular object is J1655-40, and no, you don't have to remember that. This is actually an artist's rendition of a signal that was observed by the Chandra X-ray Observatory, and it's an artist's rendition because we don't really see black holes. They are black. We can only infer that this black hole was here because what we do see are these jets of light that are being ejected outwards as this black hole accretes matter. So one thing you should know about black holes is if a black hole just sits in empty space, it is black. You won't see it because it has so much gravity that even light can't escape. But when it's sitting in some soup of gas and dust, and it's accreting that, what basically means that material is falling onto it, that material heats up and that material glows. So we only see it because of the glow of the material that the black hole is eating. The jets are due to the fact that the black hole is actually a very sloppy eater. So as it eats things around its belly, it spews it out of its head and its toes. That's what it's doing. And that's how we see black holes, okay? Now, it would be really nice if one could directly observe a black hole and not have to rely on the few black holes that are accreting material from a companion star and so on. And that's where a new messenger can be useful because we know that the black hole won't emit light. And that's where gravity's messenger would be very helpful to have. So what do we know about gravity's messenger? So way back when, in the 17th century, the first hero of gravity was Sir Isaac Newton. And Newton actually had this incredibly successful view of gravity. Newton, and we've all at some point experienced Newton's gravity because we can take an apple and it will drop down and fall because of the gravity of the Earth. Now, Newton's idea was that any two objects that have mass, m1 and m2, will feel a mutual force of attraction due to gravity that's proportional to their masses and inversely proportional to the square of their distances. And that actually, it turns out Newton not only formulated this idea, but this is one of the first equations of physics that we learn and one of the first equations of physics that was written down in this formal way. Now, turns out Newton really worried about a problem as well, and this is called the problem of an action at distance. A very successful theory, by the way, because in Newton's time already, you could use this equation and the math behind it to predict the orbits of planets around the sun and of moons around planets, etc. But Newton worried about this question of how does this object of mass 1 know about the object of mass 2? How do these two objects, how does our Earth know that about the sun and to orbit it? And this is called the problem of action at a distance. How does information travel between these two objects? And that conundrum didn't get solved until our next hero of gravity came along in the early 20th century, and that was Einstein. Now, Einstein said, you have to forget about the idea that gravity is a force. So all of you students who have learned that gravity is a force, you have to look at your science teachers and know they lied to you. Okay? Really, gravity can be thought of as a force in certain situations, but Newton's idea was that gravity is geometry. So what does that mean? That simply, in Newton's picture, Newton said all of space-time is a flat membrane, a rubber sheet, if you like, or the surface of a cushion. And when you put a massive object in that empty space, this is simply the same as saying if you put a bowling ball in the center of a cushion, then the cushion surface will curve because of the bowling ball. And now if you put a playing marble at the edge, that playing marble has no choice but to fall into the bowling ball because it follows the curvature of the cushion. And that was Newton's idea of gravity, that the force of attraction, if you will, was nothing but the playing marble following the curvature of space-time. And Newton also wrote an equation, and it also looks quite benign. It looks an equation rather like Einstein's equation, but in Newton's equation, he was connecting the mass of the object to the curvature of space-time. It's a geometric equation. It looks really quite benign. It is perhaps the most beastly equation ever written. And so what's hidden inside of it is that it is not one equation, but many equations. And it has taken the better part of a century to find exact solutions for this equation. So when you talk about patience, there's the first lesson in patience, that the discoveries that come out of Einstein's equations took a long time because the equation was pretty hard to solve, okay? Now, Einstein asked another question as well. He asked the question, what if the bowling ball doesn't just sit on the surface of the cushion? What if the bowling ball is bouncing? Then what happens? And what he found out of his equations was, and out of our own intuition you might imagine, that the surface of the cushion would ripple. Very much like if you dropped a rock on the surface of a still pond, you would see ripples, and those ripples would travel outwards from where the rock was dropped. And that was the picture that Einstein formed from his mathematical theory of a gravitational wave. So here would be curvature of space-time if the object was sitting still, and if it were actually, if there were two objects that were orbiting each other, or if they were moving, accelerating, you would see these ripples that travel outwards on space-time. So here is now the thing that's lesson number 2. Empty space, space-time collectively, as Newton taught us about, doesn't just sit around. It can warp, it can ripple, and in some cases at the bottoms of the funnels of black holes, it can even tear. So space-time, so the next thing you have to know is space-time isn't as sweet as it looks. It does very violent things. All right, now Einstein himself, this came out of his theory. He was the one who came up with this idea that gravitation exists. He was very ambivalent about this the whole time. So he formulated this complete mathematical theory for gravity and gravitational waves between 1915 and 1918. In the first paper that he wrote, he actually got it wrong. He corrected it in 1918. In 1918, Schwarzschild, was another physicist, actually used Einstein's equations to propose that there were stars with so much mass and such a small volume that even light couldn't escape their gravitational pull. And Einstein and Schwarzschild had a correspondence. Einstein did not like these dark stars. They were called dark stars at the time. Now we know we call them black holes. Now, Einstein actually vacillated not just about dark stars, he also really vacillated about the gravitational waves themselves, not just that they were very faint, which he had understood, but did they exist at all? And in 1936, he actually wrote a paper in which he asked the question, do gravitational waves exist? And his answer was no. He submits this paper, and then a short bit later, he retracts this. So he submits a retraction of gravitational waves in this paper in 1936, and then he retracts the retraction. So you can see that this was not all clear for him, and you can understand why. He was proposing that space-time is extremely peculiar. But finally, the doubts and controversy actually died down in the late 1950s, and after some famous gathering of physicists. Now, I myself am an experimentalist. I build experiments to test what nature does. So I feel very proud to tell you that in the end, none of this mattered. The only thing that matters is experiment and observation. They always have the final say because that's what nature does. Right? I mean, you still have to build a good experiment. You can't just smack it together. But if you build a good experiment, you will tease out what nature really does. Okay? So what evidence mounted for Einstein's gravitational waves? So in 1934, Body and Zwicky, two physicists, proposed that there could be these bizarre objects called neutron stars, which I've already introduced to you. It's an object that's made up entirely of neutrons. It's the mass of our sun, and it's 10 kilometers big, so very dense object. In 1967, Pacini and Gold actually proposed that not only could you have these neutron stars, but they should be spinning very rapidly around their own axes. And when they spin very, very rapidly, they form something called a pulsar. So normally, if you take a light bulb, it's shining light in all directions, like our sun shines light in all directions. But these very rapidly spinning stars actually shine pencil beams of light. The light is very beamed, like lighthouses. So every time the light beam crosses our line of sight, we should see a pulse of light. Shortly after this, the first pulsar was discovered in 1967 by Bell and Hewish. In 1969, this man, Joe Weber, actually takes the world by storm by saying he has discovered gravitational waves. And the claim was made using an object like this, which is a big, it's about a ton of aluminum that was supposed to be set off ringing when a gravitational wave passes through it, and he would be able to measure the very tiny, it's like a wine glass, when you clink it, it rings, but this was a metal bar, and that would be a gravitational wave detector. Now, it turned out that this measurement that Weber announced was never repeated by many others who tried, and eventually was found to be incorrect. But it did actually get interest going in the idea of gravitational waves. Now, why was this a special time for this? It was a special time because in Einstein's time, we didn't know about neutron stars and black holes. And as soon as we learned about neutron stars and black holes, the first black hole was discovered in 1971, people started to wonder if there could be gravitational waves that are measurable. And then the final sort of evidence came when a pulsar was discovered in a binary system. So now here is a system where there's two neutron stars orbiting each other. And when you have that, then you see the lighthouse pulse from the pulsar, and you count it, you time it, and that timing would be disturbed by the fact that it was in a binary. It had a companion. And they measured the timing of that, and they found, remarkably, that these two neutron stars that were orbiting each other were getting closer and closer to each other. Now, our Earth has been orbiting the sun for 4.5 billion years. We are not getting closer and closer to the sun. We go, every time, once per year, we come back to where we were. And neutron stars in this system were a little bit different. Why? Why were they getting closer to each other such that in about 200 million years, these two neutron stars would actually collide? And the reason was that they were following Einstein's relativity, and they were emitting gravitational waves. And like all other waves, gravitational waves carry energy. Where does that energy come from? It comes from the orbit. So they had to get closer and closer to each other and eventually collide. And this is what Hulse and Taylor measured. They measured, this is a curve where on the horizontal axis is the year. So it was discovered in 1974, and they measured it for decades. And on the vertical axis is just the size of the orbit. The fact that it's growing smaller fit exactly the prediction of Einstein's general relativity if these were emitting gravitational waves. And this greatly impressed Sweden, and they actually won the Nobel Prize for this discovery in 1993. And that settled the question, do gravitational waves exist? But this was still not a direct measure of gravitational waves. We measured the light pulses to infer that the gravitational waves must be emitted. All right? Then Einstein's ambivalence was completely justified, because if you took ordinary stars as were known in Einstein's time, they could not emit enough gravitational radiation to be measurable. The first evidence for neutron stars and black holes came after his lifetime. And the thing to me, as someone who's looked at this carefully over my career, the most remarkable thing is that he was ambivalent. He didn't know about neutron stars and black holes, and yet he made a theory that made extremely precise and firm predictions of what space-time should do when there were neutron stars and black holes present. And let me show you. Now I'm going to fast forward from Einstein, who told us this in 1916, to something around 2006, when there were major breakthroughs using supercomputers and very sophisticated mathematics to solve Einstein's equations. The one I told you was very mean, for the case of two black holes that were orbiting each other. So what you're going to see in this movie is the surface you're going to see is space itself, and you're going to see the two black holes orbiting and getting closer to each other, and then on the bottom you'll see this signal that would accumulate as the space ripples and the waves go out towards us. So let me play the movie. So you see the two black holes, and when they're far apart, all you see is each black hole warps its own space. It's just a funnel under each black hole. And then as they emit gravitational waves and shrink their orbits, you'll see that their funnels, their space-time starts to merge, and the funnels get closer together. And then you'll notice that the warpage of space-time starts to grow as they get closer and closer. Not only do you form the funnel, but now these two funnels start talking to each other because they're getting close enough, and you see very warped space-time. And watch at the bottom, see the signal accumulating. And eventually, the two black holes, their horizons, the black shroud they live in, will actually touch. And that's the moment at which you will see the most spectacular warpage of space-time. You will see the maximum signal. And then the two black holes will merge and wobble a little and become a single black hole. And then the gravitational waves that were emitted in that process will emit out into the universe. Okay, that's the process. Now, before 2006, you could not make animations or movies. This is a movie that's made out of an exact solution to Einstein's equations through a very extensive collaboration to solve Einstein's equations. So now that we have that in 2006, but it wasn't always so good. We didn't always have the ability to know what Einstein's equations would do. Back in the late 1960s, this man, Kip Thorne, you've met him once before. He's the Nobel laureate that I showed you. And you might have come across him in one other place. He's also one of the masterminds behind the movie Interstellar. Okay? So Kip Thorne, this is now right at the time of the discovery of neutron stars. And so Kip asks the question, well, if you really have neutron stars and they really are in orbit around each other, and if you put them in a galaxy not too far from our own, what would we see here on the Earth? And Kip was one of the first people to show that you would see, let me show. You would see a signal like this, which you've already encountered with the exact solution I showed you in the movie just a minute ago. And Kip also put, for the first time, a scale on this. Kip said that the size of this wave would be 10 to the minus 21. Now, you're going to ask, that's a terribly, terribly small number, right? That's a decimal point with 20 zeros after it before you put a 1. So it's a small number, but at the moment, you shouldn't be too alarmed because I haven't put any other scale on it. Is it 10 to the minus 21 meters? Is it 10 to the minus 21 kilograms? There's no scale on it, and the reason for that is that it is a dimensionless number. It's actually a change in length per length, and I'll explain that in just a moment, what that means, okay? So Thorne and others, through their work, we understood what would make a good gravitational wave source. So I don't put too many equations in my talk, but here is one equation for the equation junkies because it's very cool. So what this equation says is the luminosity in gravitational waves. That's how much power. It's basically like if I have a light bulb, how much wattage do I have? The luminosity in gravitational waves scales with some constants of nature, but then it scales with this quantity R, Schwarzschild over R, which really is the mass of the object. It's basically saying, if I have an object of a certain mass, whose radius is the radius of a black hole of the same mass, that would be the Schwarzschild radius. So the first thing you see from this equation is that if you want to have a very gravitationally luminous object, you need an object that's like a black hole. Its size has to be comparable to a black hole for a given mass. So for our own sun, for example, it would have to be the size of a few centimeters before it would be a good gravitational wave source. And then the other ingredient we need is this V over C. V is the velocity of the stuff in the object moving around, and C is the speed of light, and that's to the 6th power. And what that says is that you need things that are moving very, very fast. You want that to be fast. So now you know you need two ingredients. You need the object to be very compact, and you need it to be relativistic. And that's why you need it to be a neutron star or black hole and not an ordinary star. And you also need it to be accelerating, so it needs to be in an orbit or exploding or colliding. If you just take a black hole sitting around in space doing nothing, it will not radiate, okay? And so we can imagine that black holes and neutron stars are good sources. Turns out supernovae, like the one I showed you of the exploding star, would be a good source of gravitational wave. And then there's one source of gravitational waves that's very, very difficult to observe because they're very, very faint. But for me, I would say this is what got me into the field. It's my most favorite source. I don't think it will be seen in my lifetime, but I'll tell you about it because it's the most amazing thing. So during the Big Bang, we believe gravitational waves were given off, as was light and as were particles made. Now, it turns out when we look back at the history of the universe, the very first time that we can see what happened after the Big Bang is the cosmic microwave background, which is light. Now, light, it turns out, is very, very friendly. When the universe was hot and young, the photons and all the electrons and protons, they all lived in a small volume. It was very hot. And every time a photon met an electron, it would hang out and chat and get deflected and scattered. So here's the analogy that might work well. Imagine you go to a party and you trying to leave, and you want to, and you went there with an extrovert. And you say, okay, I'm ready to go. And by the time you actually get out the door, it's an hour because they stop, they meet everyone, they chat a little, and then eventually they make their way out. That's what photons were in the early universe. They met electrons, they would scatter, they would absorb, they just wouldn't escape that hot soup. Gravitational waves, on the other hand, are extremely aloof. It's the exact opposite. You go to the party with an introvert, you're lucky if they say thank you to the host before they leave, and you're out the door. And that's what gravitational waves are. They were streaming out from the beginning of time. So if you want to see the universe when it was really being born, light is not your friend. The first light that we can see came from the universe when it was 400,000 years old. And if you want to see the universe being born, you have to do something other than light, and then gravitational waves would be your friend. Now, why am I pessimistic? Because these are extremely faint, even fainter than the gravitational waves that we would see from neutron stars and black holes. Okay? But that doesn't mean we shouldn't dream. Okay. Now, at the same time as Thorne was telling us about how what signals we might see from gravitational waves from these neutron stars and black holes, this man, I should tell you a little bit about what gravitational waves do before I tell you about how I might detect them. So you can ask the question, so now you know gravitational waves are emitted by these black holes and neutron stars and also by the early universe, but much fainter. Now you might ask, what do they do? So we know from Einstein's theory they're ripples of space-time. They travel at the speed of light. So they're rippling and they're traveling at the speed of light. A very important characteristic for our purposes, a property, is that they stretch and compress the space-time itself as they travel. So how do you understand that? The easiest way is to visualize if I were a space-time object, what they do is they change the distance between space-time objects. So imagine me, all of us are space-time objects. So I'm a space-time object, and I'm a space-time object of length L, okay? If a gravitational wave came through me right now, what it would do is that in each cycle of the gravitational wave, it would compress me in one direction and stretch me in the other, and in the half cycle later would do the other thing. So if I was a gravitational wave were going through me, this is what I would do. I'd go shorter and squatter, and then I would grow longer and slimmer. That in each half cycle of the gravitational wave. And at the frequency of the gravitational wave, if a fast wave was coming, I'd be doing this. If a slow wave was coming, I'd be doing this, right? And all of us, this would be happening to all of us. And by how much? Now that's where the real trouble comes. If I'm an object of length L, then my length would be changing by an amount delta L that's proportional to my length and proportional to the amplitude of the wave. And now you should really sit up, because I already told you what Thorne told us about the amplitude of the wave, right? Thorne told us that the amplitude of the wave was 10 to the minus 21. And now you can see I'm a space-time object of order a meter. So when that gravitational wave goes through me, it changes my length by 10 to the minus 21 meters. That is 1,000,000 times smaller than the single proton. No wonder we don't feel gravitational waves, right? Okay, so that's the rub, and this is what made Einstein so pessimistic, because he did not have a number of 10 to the minus 21. That's from neutron stars. He looked at ordinary stars, which are another factor of many millions smaller, okay? But this man saw something special in this process that the gravitational wave stretches and shrinks space-time. So Ray Weiss, then now Professor Emeritus then at MIT, he said, well, if a gravitational wave stretches and shrinks space-time, we should be able to measure it. And he proposed this device. It's called an interferometer, and that's the I in LIGO, by the way. He said, take a laser, split it in two halves, and send one half of the beam along one direction, and the other half of the beam at right angles to it. Put a mirror at each end, reflect the light back, and then measure at the output here. And the process is that when the light waves from this direction, from one direction, add up with the light waves from the other direction, you would see a lot of light at the output. And when they cancel, you would see no light and everything in between. And whether they add up or they cancel simply depends on whether the two lengths were equal or unequal. So this is a way of telling when the distances from the laser to each mirror is the same or not. Now, you can arrange the experiment so that the distances are exactly the same, and then when a gravitational, and so you see no light, and then when a gravitational wave comes by, it actually will change these distances, and then you will see the light pouring out of this detector. Now, Weiss understood one other thing very importantly. He understood that you could not make this device just about a meter long. Remember, a meter long would be us, and that's 10 to the minus 21 meters, and we have no idea how to measure such a small distance. So what he proposed instead was that you have to make the detector kilometers long. You have to make it thousands of meters long. And he proposed a 4,000 meter long detector. And in that case, you have to measure changes in the distances between the mirrors at the level of 10 to the minus 18 meters, which is only 1,000 times smaller than a proton. And he said, yeah, we can do that. And he said that in 1972. Okay? Then, in 1975, Thorne and Weiss meet, and they conjure up the idea of actually doing this experiment. And out of that was born the concept of LIGO, which is kilometer-long detectors with these laser interferometers. And now these are not cartoons. These are real pictures of a LIGO detector, of the two LIGO observatories, one in Washington State, east of Seattle, and one in Louisiana, sort of halfway between Baton Rouge and New Orleans. And you can see the concept was these L-shaped detectors with laser beams, and the real thing is the same. It's these L-shaped detectors with kilometer-long arms where the laser beams propagate. Now, to make LIGO work, you need 2 factors of a trillion. Look, I'm taking you from the smallest numbers you've ever heard of to some very big numbers, right? The gravitational wave is really, really tiny, but the task at hand is really big. So what do I mean? So what does LIGO do? LIGO's measurement is I have a mirror. I have these mirrors that are set 4 kilometers apart. And when a gravitational wave comes by, it moves those mirrors by 10 to the minus 18 meters. And I want to measure that. Now, if I just plop a mirror down on this table here, or on the floor here in a room, can you guess how much it would move by? So I'll tell you, it would move by something on the order of a few tens of microns, which is about 10 to the minus 6 meters, okay? But the gravitational wave moves it by 10 to the minus 18 meters. So there's your first factor of a trillion. You have to shield the mirrors from all external forces by a factor of a trillion. And we do that with 2 technologies. One is that we use active vibration isolation, where we measure the motion of the mirror and then cancel it out. And then we do something else, which also sounds very bizarre. We take the mirrors of LIGO, and we hang them as pendulums. So literally, you take this 40-kilogram piece of glass, and you hang it from fibers. And this is a very good lesson for all of you. Imagine for a moment that you lived, your bed was on top of a garage door. And every time your unthoughtful neighbor comes home at night, the garage door opens, your bed vibrates, and you wake up. What could you do? Well, what you would do is you would measure at what frequency the garage door vibrates your bed, and then you would hang your bed from bungee cords or fibers such that the natural frequency of rocking of the bed when it hangs is much lower than the frequency at which the garage door rumbles. And then when the garage door rumbles, your bed, the bungee cords would shake, but that motion would not go down to your bed, and you would sleep through it, okay? That's what you would do, and we just apply that in a very technical way to the LIGO mirrors, that idea. Now, I will tell you one other thing. Most people actually get woken up by the sound and not by the vibration. So if you want this to work for your garage door and bed, use earplugs as well, okay? So now we have a mirror that's really, really still, okay? We've done that. That would do you no good if you also didn't have a method of measuring very, very small motions. And that's where the laser light comes into play, and that's the L in LIGO. The wavelength of the laser that we use is about a micron, or 10 to the minus 6 meters. And now comes the second factor of a trillion, which is that the motion we want to measure is 10 to the minus 18. So now here's the conundrum. I have a ruler whose tick marks are 1 trillion times farther apart than the measurement I want to make, okay? what do I do? And the way that we get around that is we use lots and lots and lots of photons, very powerful lasers, so we can average over all of the different, over many, 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 many wavelength cycles. And that's the trick we use in LIGO, which is we use a very powerful laser, and we eventually have almost a megawatt of laser light circulating in the arms of LIGO. Okay? So now you know how to build LIGO, and you also know how to get a good night's sleep. So this was funded over 40 years since Thorne and Weiss got together by the National Science Foundation. And here also comes the third of our Nobel Prize winners, Barry Barish. I got ahead of myself. This man here. And he's credited with actually, he was the director of the observatories and is credited with actually building the observatories and getting the experiments running in an organizational way. And I want to take a small little pause here because everything I'm going to talk about beyond this point is actually going to be otherworldly. So I want to bring us back to this world for a second. Keith, when he introduced this talk, talked about patience. And here's the patience, which was that this was, the first signals we detected came in 2015, and this started in 1975. So it's 40 years of investment by the National Science Foundation, by the political system, because this actually was built by funding that was a line item in Congress. And the question is, how do you do that? How do you make that happen? And part of it was consensus. So Thorne and Weiss spent the first decade of this building consensus among the scientists, saying it's a good idea to do and it can be done. And then there was this process of also bringing, educating, of scientific education of politicians and sort of civic engagement, if you will. And I pause to say this because I also just want to remind everybody, vote in 3 weeks, 4 weeks, whenever it is. Please go vote. It's really important. This stuff only happens when we vote, okay? Yeah. Thank you, but you haven't even seen the coolest thing as I still have to show you, okay? All right, so they started LIGO. In the meantime, other observatories have popped up nationwide. And so here are the two in the US, the two LIGO detectors. There's a 3-kilometer detector, a gravitational wave detector in Europe called Virgo. There's a 3-kilometer long detector in Japan that's under construction still called Kagra. And then there's a planned detector in India that's still being planned, and also a planned space detector called LISA. So this is the global network of detectors that have come about since those early days of Thorne and Weiss. So now we fast forward again from the 1970s to 2015, which was the first time, September 14, 2015, was the first detection of a binary black hole collision by LIGO. And so what happened then? So here is an animation, this is now not a movie, of two black holes colliding. And as they collide, you can see they gave off these gravitational waves that traveled across the universe. And as they go through the universe, remember I told you gravitational waves are very aloof. They don't interact with anything. So they basically pass through all these stars pretty much unchanged. And then a billion years later, they happen to pass by our beautiful planet. And here is the discovery that shook the world. Now, I will say, as you now know, it didn't do this to our planet. It actually shook our mirrors by a very tiny amount, and you know what that amount is, and if not, I will tell you in a moment. So this signal registered first in our Louisiana observatory, and 7 milliseconds later, it registered in our Washington observatory, and here are what the two signals look like. And I want to just draw your attention to a few things. This is now a very iconic plot. On the horizontal axis is time. This signal that we measured with LIGO lasted 200 milliseconds. On the vertical axis is the amplitude of the gravitational wave, which, by the way, is called strain. It's that quantity h that I've been telling you about because it's a change in length per length, so it's called a strain. Now, there's some amazing things to notice. There is a scale, 10 to the minus 21. When those two black holes touched, which is the maximum of the signal, we measured a strain of about 10 to the minus 21. So it's an enormous check mark for Kip Thorne. He told us this in the late 1960s, that this is what we should see. When that gravitational wave passed through our detector, our mirrors were displaced. They moved by a few times 10 to the minus 18 meters. Enormous check mark for Ray Weiss. He told us how to do this in 1972. Okay? So you can see these guys should get a Nobel Prize, and they did. Okay. Now, what can we tell from these signals? What does these signals mean? So this is the exact signals that I showed you that we measured, but this is a model of that signal. And I want to show you how do we understand what these were. How do we know they're black holes? What do we know about them? So it turns out that by looking at the frequency change, by seeing how this wave's frequency is changing with time, we can tell what the mass of the objects was. And that told us they were very heavy. Once we know that, by looking at the amplitude of the wave, the height of it, we can tell how far they were. And then finally, by looking at this last part of the signal here, where the wave is kind of decaying, you can tell what the mass and spin were of the final black hole that was formed. The two black holes collided, formed a new one. How heavy was that? And from this, we can reconstruct the life of this little black hole pair. So this is a story of two black holes. Once upon a time, 1.3 billion years ago, there existed two black holes. And they were in orbit around each other, and they were emitting gravitational waves. Now, I like this simulation a great deal. Again, it's an exact simulation, but it's been put in a star field. These black holes were not in a star field, but if they were, you would see all this starlight being deformed by the gravity of the black holes. And I like this animation in particular because it's the same animations that were used in Interstellar. So Hollywood is useful sometimes. Okay? Now, what we find was that looking at that process and what the final black hole was, we found something really remarkable. The final black hole was 3 times the mass of our sun, lighter than the two original parents. So 3 times the mass of our sun was emitted in gravitational waves in that 0.2 seconds. It's kind of a remarkable thing. And what it says is the following. It says that the mass of the black holes was 30 times the mass of our sun. At the moment that these two black holes touched each other, they were moving at half the speed of light. You just have to stop and think about that. Something that's 30 times the mass of our sun, 250 kilometers in radius, moving at almost the speed of light. If you write science fiction, you couldn't probably come up with that, right? They were 1.3 billion light years away, and they lost 3 times the mass of the sun in those 200 milliseconds, which means it is the most powerful explosion we've ever measured since the Big Bang. Okay? So it's a pretty spectacular thing. Now, what we know is that the two black holes did not live happily ever after. But I'll tell you one other thing that's very important. Out of their sacrifice was born this new black hole. So very much just like parents do, we give ourselves up for the new ones that come around, right? Black holes, the life cycle of stars is not that different, okay? All right. Now, in the meantime, a handful of other collisions of black holes have been detected by LIGO and eventually Virgo as well. So now I'm going to fast forward to 2 years later. So the year 2017, the 8th month, the 14th day, so 14th of August 2017, we saw a black hole collision that was for the first time also seen by our sister observatory Virgo in Europe. Now, why was that so important? So this is, I won't bore you with the details. It just shows there are 3 curves here that shows that all 3 instruments were operational. The purple curve here is Virgo, and it just shows that Virgo wasn't quite as sensitive as LIGO. The lower the curve goes, the better the instrument is behaving. This black hole collision was seen by the Washington, the Louisiana, and the Italian detector with different strengths. But the most remarkable thing about this was that gravitational waves, you must have heard some of these analogies of gravitational waves are like listening to the sounds of the universe. And I'll tell you where that comes from. It's not really that the universe is making sounds. Remember, space is a vacuum. Sound wouldn't travel. There's no substance for sound waves to travel. Where this analogy comes from is that gravitational waves that we are trying to measure here on the Earth from these neutron stars and black holes happen to be in the human audio band. So when I take that set of bumps and wiggles and this set of bumps and wiggles. And if I put those on a microphone, I would hear it in my audio band. That's why we call it sound. But the analogy is useful for one other reason. Gravitational wave detectors are very much like our ears. They can't localize the source very well. You know, if I shine a laser pointer up here, your eyes can very well tell exactly where this laser pointer is shining. If I shine a second one close to it, you can tell those two apart very well, right? If instead of laser pointers, these were little loudspeakers where I was making sounds, you wouldn't be able to tell which loudspeaker was making the sound because your ears can't resolve it. Gravitational wave detectors are the same, and that means we have two ears because we triangulate sound. And so the more gravitational wave detectors you have for triangulation, the better you can tell where the source is. So here's what happened then. So for all the black holes that LIGO alone had seen, you see these big patches of sky where they could be. We don't know where within this big patch the black hole collision happened. And that's very, very problematic, because if we want to tell our astronomer friends to point their telescopes at this, they won't know where to point. They have these patches are too big to cover with telescopes in a reasonable amount of time. And then with this, with Virgo online, look how well we were able to localize this. This is a small patch of sky that any telescope would point to. And in fact, with just the LIGO detectors, we would have localized this to a 1,200 square degree patch. But with Virgo on board, it was a 60 square degree patch. So you can see it really matters if you have a third detector on the air. And that was very nice, but we know black holes are black. You point a telescope at it, you're not going to see much. But then 3 days after this, remember this was August 14, 2017, 3 days later, something incredibly spectacular happened that I'll come to in a moment. In the meantime, LIGO and Virgo have seen all these different black hole collisions, and all of them, you can see they last of order less than a second or so. The signal lasts in our detectors. And you can see they have different amplitudes that depends on what their masses of the black holes were and how far they were. Now, we've answered some questions already with these 5 black holes that we've seen. We've seen that Einstein's theory of relativity seems to be correct. We've seen that gravitational waves seem to travel at the speed of light, and they seem to have the right geometry. So these are also big check marks for Einstein. We've seen black holes exist. This was a big question, and that they form pairs. That is also something we've seen. What we were surprised by is we don't know how nature makes such heavy black holes. We know how nature would construct black holes that are 3, 4, 5 times the mass of our sun. We don't know how nature will construct black holes that are 30 times the mass of our sun. This is one of the beauties of discovery. All it does is you ask a new question, right? We also don't know how they form pairs. And we're just starting to tease that out by looking at the spins of black holes, because black holes are spinning about their own axes. And if they were born as twins, then their spins should be aligned. And if they were born as individual black holes that captured each other, then their spins should be misaligned. And that we're just starting to get evidence that for one or the other. Now, 3 days after that triple detection with Virgo, something even more spectacular happened. Well, it's arguable. It was something very spectacular, which was the first binary neutron star. Now, neutron stars, remember, they're cousins of black holes, but there's something very special about neutron stars. They're made of neutrons. They're not black. When neutron stars collide, that's like a big nuclear reaction, a big collision of particles, and it should give off lots and lots of light. It should fuse lots of chemical elements. So LIGO and Virgo saw a binary neutron star collision, and that was followed by a technicolor light show that was observed by over 70 telescopes worldwide. So what happened? Here is what LIGO saw. LIGO and Virgo. And the first thing you notice is, look at the time scale. All the black holes I showed you were about a second. This signal lasted a minute. And that immediately told us these were light, and therefore they were neutron stars. They're not heavy like black holes. About 1.7 seconds after LIGO and Virgo saw the signal, a very bright gamma ray burst was seen by the Fermi Gamma Ray Telescope. And these gamma rays are photons that are emitted, but very, very, very high energy photons, which you would expect from a neutron star collision. So with these two observations, the LIGO, Virgo, and gamma ray community sent out a notification to telescopes worldwide, we have seen something. And we could localize it pretty well, because Virgo was on the line. We could localize it to a 30 square degree patch of sky, which turns out to be in the southern hemisphere, and our detection happened when it was daytime in the southern hemisphere. So astronomers had 12 hours till night came to the southern hemisphere telescopes to plan to look for this. And then came in what I would call sort of a physicist astronomer's night to remember, which was that all these telescopes turned, and this is a very, very busy slide. I want you to only notice a few things. Whether you look at it in gravitational waves, or gamma rays, or X-rays, or ultraviolet, or optical, or infrared, or radio, every wavelength of light saw it, saw an object. Now, what do I mean by see an object? Here is a set of telescopes that were pointing at this galaxy, NGC 4993. And notice that this crosshair is on this little dot. Every one of these images has the crosshair with the dot, all these different telescopes. This is what this telescope saw 20 days earlier. Nothing in the crosshair. A new object had lit up in the sky. And that's what you expect. The process for these neutron stars, I'll show you in a little animation, is that the two neutron stars were orbiting each other. They weren't giving off any particular light. They were giving off gravitational waves. And then eventually they collided. And in that collision, the light was given off, and the object lights up for a telescope. So here's what happens. Neutron stars are orbiting. Only gravitational waves being given off, which is the blue. Then they collide dramatically, as the music will imply. Jets of gamma rays go off, and then in the center where all the neutrons are colliding, you see the light. And this is the process that we saw with all the telescopes that night and for many weeks after. Okay? The very first thing we saw were those. Would anyone like to see it again so you can see the jets of light that came off? The gamma rays are jetted. Remember, that's the materials being blown off the head and the toes. So I'll play it one more time so you can see the process. So gravitational waves. And then notice the jets will be just two jets. And then in the center will be the neutrons that give off all the optical light. There we go. Gammas, optical. So, with this object, well, that's the NASA special effect. Okay. Now, this is a picture. Notice this. This is showing, look at this in days. What this is showing is different colors of light. These are different wavelengths of light. And as we measured this object over a number of days, we saw different peaks, light in different colors show up and other light turn off. And this process, every one of these peaks of light corresponds to the fusion of elements. So what we are seeing here in real time is gold and platinum being fused. In the collision of these neutron stars, these neutrons, when they collide, they form the nuclei of very heavy atoms, and those are gold, platinum, and the heavier elements. And this is, and this is why this object has also been called nature's gold mine, because you're seeing gold being formed. Now, why is this so special? I will tell you why we were so fond of that. So it solves a decades-long mystery. A few decades-long mystery. The first one is that for a long time we have wondered if the collision of neutron stars is the cause of these particular kind of gamma ray bursts. We've been seeing gamma ray bursts for 2 decades and haven't known what causes them. And this is the first time by seeing LIGO see the neutron star and Virgo see the neutron stars collide, and then the gamma ray telescope seeing the gamma rays, we now know that the gamma rays come from the collisions of neutrons. Another long-standing mystery is, you won't believe this, but here on the Earth, we have too much gold and platinum. What do you mean, too much? Well, it turns out it's more than we think could be fused in our sun, which is where all the elements we're made of tend to come from. It's more than we think could come from supernovae explosions. We have just more gold and heavy elements here than have been deposited by the formation of our solar system from just the sun. The sun fuses elements, but it doesn't have enough neutrons to fuse the very heavy elements. So where does all the gold and platinum, not all, but about 80% of the gold and platinum come from? And now for the first time, as I showed you in the last movie, we saw nature making gold and platinum in the collision of neutron stars. So the first time we've understood that this gold and platinum that we haven't known where it comes from neutron star mergers. And the last thing that we could tell by this collision of neutron stars is for the first time we can see light from an object and gravitational waves from the object. And by looking at the gravitational waves and at the speed at which they propagate, we could calculate something called the Hubble constant. Now, you will say, oh no, she's going to give me another a little bit of nerd memorabilia. But no, the Hubble constant is not nerdy. It really matters to you, and I'll tell you why. The Hubble constant determines the history and the future of the universe. So you should care, okay? And using different techniques with light, there has been a discrepancy on what the Hubble constant exactly is. Two different methods have given two different answers. And we've made an independent measurement now with gravitational waves, and our answer is quite inaccurate still because we only have one object to look at, but it comes in the same ballpark as the other two. So our universe is safe. Even with gravitational waves, we think it's going to do what it's going to do. Okay? So these were some of the decades-long mysteries that were solved. Now I'm going to skip telling you about Lisa. I'm going to tell you what, I want to point out that I think you're witnessing a new era. I told you we are opening a new window into the universe. What was that window? The window was that we no longer use just light, we can use gravitational waves. So what's all the excitement? Well, this is the first direct observation of gravitational waves. The first time we see you see the signal? This is a measure of the bumps and wiggles of space-time itself. Directly we're measuring that space-time can ripple. Einstein's general theory of relativity seems to be working in this regime where it's never been tested before. Black holes and neutron stars occur in pairs, and they actually collide, and we can observe those in real time. And then let me tell you, I told you a little bit earlier, I'm an experimentalist. My role has been in building these instruments. I have to tell you, it's really nice that the goddamn instrument works as well, with the precision that you needed. Not just it works, but it works precisely enough. Okay? So these are the sort of the triumphs of this moment, of the last couple of years. But I want to leave you with this idea that that's not what that's not what the generations will remember 100 years from now. What we've really done is we've turned on a completely new way to look at the universe, something that humans have never been able to do before. And because of that, because we can now use gravity instead of light, we can start to observe objects in the sky that don't give off light. Black holes may not be the only thing. There will be other things that will be discovered. So I'll leave you with this one last thought, which is that Galileo, we believe, was the first person to point a telescope at the sky in 1609. And the telescope that he pointed at the sky was a small 1.5-inch refractor. Most toy store telescopes today have greater capabilities than that. And most people don't remember what Galileo saw. He saw that Venus has phases. He saw craters on the moon. And we've seen those things much, much more precisely now. But what Galileo is remembered for and should be remembered for was the paradigm shift. Galileo was the first to tell us, humans, you do not need to use just your naked eyes. You can use instrumentation to look into the sky, and with that capability, we've made discoveries that our eyes could never make, right? Since Galileo, we've made, from that 1.5-inch telescope, we've made 100-inch telescopes. By the early 20th century, nearly 100 years later, we put 100-inch telescopes in space. There's the Hubble Space Telescope. We're now building 25 to 30-meter class telescopes. And in the meantime, we've also turned on all different colors and wavelengths of light that our eyes can't see: infrared, gamma rays, X-rays, radio. And that's been the progression in the 400 years since Galileo told us, build a telescope and look into the sky. And I believe that's where we are with gravitational waves. Gravitational waves are just like light waves. They span 20 orders of magnitude in color, in wavelength. And we've only seen these fastest waves here with these ground-based instruments. And there's a whole slew of other measurement techniques for looking at other wavelengths. So I believe if you stay tuned in, you're going to see a revolution where we'll see the sky and therefore the universe with gravitational waves that we've never seen before. And that's what you should be excited about. Thank you.
So I'm sure you all enjoyed that very exciting lecture, and we have some time for some questions that you can ask Professor Malvalvala.
Please. Sure, I'll repeat it.
So, I was thinking, this very powerful laser is hitting this mirror. Does the mirror heat up?
Yes. So the question is, when this very powerful laser is hitting the mirror, does it heat up? Yes, it does. So our mirrors, as you can guess, are actually made of some of the purest glass you can find so that the absorption is low. But even then, it absorbs about, for every million photons that hit the mirror, it absorbs one. Okay? But even so, with it's being hit by a megawatt of light, it's absorbing a watt of light, right? And so it heats up, and it heats up in the shape of the laser beam itself. So it not only heats up, it doesn't just heat up uniformly and expand, it heats up and becomes a lens. And so we have to correct for that, and we correct for that by heating it from the other side with a heater and undo the lens that formed. But yeah, there's another thing that happens when this megawatt of light hits the laser that isn't to do with heating, which is also kind of amazing. So it turns out, light can exert a force. If I had a powerful enough laser, I could actually move things with it, and we do that, regularly in labs and so on. And so the mirror also gets pushed by the laser light. But we don't care about that because it just gets pushed to a new position and it stays there. So that's okay. But the radiation pressure also exerts a force on the mirror.
There's a question there.
Okay. Can you tell us whether eventually high-temperature superconductors will have any significant part in gravitational wave detection?
Yeah, so the question is, will high-temperature superconductors have a role in gravitational detection? So I'll tell you, the place where they might is if they become very low-noise sensors. Because what we do is, our business is we count photons, right? And so if you can think of a technology where you can count photons more precisely, then that would be a good thing. But I do not see a direct application of that right now. So.
Okay, there was a question there in the back.
How close would you have to be to the merging neutron stars to be in trouble in terms of that strain? In other words, if you were 100 light years away instead of over 1 billion?
Yeah, so let me just say a couple of things. So that's a good question. So the black holes that we've been seeing, the black holes are much more massive. We've been seeing, anything from 20 to 30 solar mass. So those are 1 billion light years away or so. It turns out that the neutron stars that we saw, they're 10 times lighter. And so for the same signal which we're sensitive to, they have to be quite a bit closer in. So the neutron star, the one binary neutron star pair that we've seen, was actually 100 million light years away. So which by astronomy standards is in our neighborhood. So, but you asked a different question. You asked how close do you have to be before which the gravitational effects would be felt in maybe a catastrophic way, like we would get ripped apart. And I think you actually have to be quite close in for that. You have to be within kilometers of that system for that. So.
Bianca? We have a question up. Bianca's going to ask a question here.
Yeah, I'll repeat it.
It is possible, will it be possible? Is it possible, or will it be possible to detect a gravitational wave that was caused by the Big Bang?
Oh, you ask a question that pains me. So the question is, would it be possible to detect gravitational waves that were you know, part of the early universe and part of the Big Bang? And the answer is, I'll give you the crisp answer. The crisp answer is that with the detectors that we know how to build today, those are 1,000,000 times weaker than the signals we could see. And I'll just remind people that it takes us roughly 2 decades to get a factor of 10. So you can imagine that it's going to, that's why I say I don't think it will be in my lifetime. There is another way to measure it that isn't with these interferometers. And that is something where you could actually look at the microwave background, the light from the early universe. It turns out the light from the early universe will be ever so slightly polarized, which means that the wave wiggles in one particular direction preferentially by the gravitational wave. So if you could measure that polarization, then you would be able to infer that the gravitational waves are there. And that's what, there's experiments are going on already right now looking for that. But it has not been seen yet. And that will be a nice confirmation that they're there. But it won't be the direct measure of the space-time ripples from the early universe. It will be an imprint of those. So, but
Another question there.
Thank you for your talk.
Thank you.
I'm wondering if you could describe what. I'm wondering if you could describe what your own research is in this collaboration, and sort of what sparked you to pursue that as a PhD student.
yeah, so that's a great question. I've done a few different things over my career. So the first thing I have to admit is that I've been involved for 28 years. So I've been involved for a long time. When I started off as a PhD student with Ray Weiss, I worked on a problem where we had these mirrors that were 4 kilometers apart, and the laser beam has to bounce between the mirrors multiple times. And how do you keep the mirrors facing each other exactly so that the beams are always bouncing and don't walk off? And this was a problem that we didn't know how to solve at the time. So that's what my PhD thesis was on. And that system, it turns out, I'm horrified to say, is still used in LIGO, 25 years later. And I'm horrified to say because I think it was actually a really brute force solution. And I keep hoping someone smarter would come up with something better. Okay? Now,
If it works, don't fix it.
no, but it's really clunky. Okay, but in the meantime, I've actually been working on a different problem than anything I've talked about here, which is related to LIGO. So, I talked a little bit about how the radiation pressure moves the mirror, the light force. So it turns out that just the mirror moving to a new location is not a problem for us. But it turns out that light is quantized, right? Light is a quantum object. It's made up of photons. And in quantum mechanics, we have to live with quantum uncertainty, which means that you cannot ever measure anything with, two particular quantities with infinite precision. So what happens here is you have this laser light that's hitting the mirror, and this laser light is imprecise. It means the number of photons in my laser beam is fluctuating. And it's fluctuating, and as it fluctuates, it applies a fluctuating force to my mirror. And now the very process of making a measurement of this mirror is shaking the mirror. This is called the quantum measurement problem, which is that the act of measuring disturbs the measurement. In lay terms, that will be called there's no free lunch, right? And so my research has been on how do you get around that, and you can actually get around that by using these very specially engineered quantum states. This is now getting very technical, but if you're really interested, I shouldn't say, but I am going to talk about that tomorrow in the physics department. So you're welcome to come, and I'll tell you about the experiments we're doing. But it's actually a very fundamental question. Even though it bothers LIGO, it's a very fundamental question, which is, if I take a particle and I shine a laser beam at it, what is the most precise measurement I can make of it? And there is a limit. There is a quantum limit, because that laser beam the quantum fluctuations are kicking the particle I'm trying to measure. So it's that. But we do experiments where we actually make these specially engineered quantum states, and we put them into the interferometer, and we make it better. So.
We have one there.
You talked about gold and platinum being formed, and I was wondering what elements beyond that were formed.
Yeah, so a large number of the lanthanide series is also in there. If you notice those spectra I showed you, the peaks were very broad. They're fairly low resolution spectra. To really go deeper, you'd need higher resolution spectra. And I think those will come in time once we've measured more of these. We've at the moment only seen one single neutron star, binary neutron star collision. But as the detectors improve and we see more, I think we'll nail that down better.
Okay. And then
Hi. First of all, I just want to thank you for your enthusiasm.
Thank you.
Makes this, it's fascinating anyway, but just watching you present it, it just makes it even better.
Thank you.
I think I have a very, very basic question. That is, you mentioned that the arms of the LIGO detectors are 4 kilometers long. How important is it that they be exactly the same length?
Yeah, so the question is, do they really have to be exactly 4 kilometers plus or minus, 10 to the minus 15 meters? No. They can be one could be 4 kilometers, and they can be a few centimeters different, and it would be fine. If it gets to be a lot more than a few centimeters different, then you actually you can still live with it, but then you have to start taking the 2 laser beams and reshaping them a little bit so that they match the shape of the arm they're in. So there's a technical detail, but in principle, what you really care about is that they're whatever length they are, but the interference itself is down at the level of a single wavelength of light, right? So that's at the micron level. So it's not very precise. So.
oh, okay. Any others? There's still one there.
There's one in the back as well.
And we have a couple here. And there's there. Okay.
If 4 kilometers is 1 million times insufficient to measure the Big Bang gravitational waves, why don't we make one that's 4 million kilometers long in the solar system, or 5 million kilometers just for our extra?
Yeah, so what I didn't tell you about was LISA, the space interferometer. LISA is actually drawn right there, the space interferometer, and LISA actually is a 5 million kilometer long interferometer. And it turns out that even though it's 5 million kilometers long, doing precision interferometry in space is actually quite hard. So in the end, LISA's sensitivity is actually quite similar to LIGO, but at a completely different frequency. LISA, so it's basically, you can think of it, LIGO as an optical telescope, LISA is the radio telescope of gravitational waves. So they work at about the same strength of source, but that they are different frequencies, which is very important because we know there are many sources that are much, much slower. If you look at these supermassive black holes that we know are the centers of galaxies, those are not whipping around at 100 hertz that LIGO and Virgo could see. Those are going at millihertz, and so that's what LISA would see. So you can make it longer and go into space, but then the precision interferometry you would need, we do not know how to do by about a factor of 1 million. So.
Okay, I saw some hands here.
Just a minute. I have a question.
Oh,
yes.
We're here. We're over here. Okay.
Yes. When you're shooting a laser through space over very long distances, how does it pass through space without bumping into gas molecules and otherwise disturbing it and making it incoherent?
Yeah. So that's a good question. So in space, for something like LISA, the laser beam is traveling 5 million kilometers, but and we know how to, and this has been demonstrated, you can make very narrow line width lasers that have the coherence length to be fine over those distances. So in LIGO or Virgo, for example, we also have very high long coherence length lasers. But if you notice, those the laser beam is actually in a vacuum tube. It's evacuated because if it does hit gas molecules, it will change the index of refraction of the beam, and therefore it will change the path length. So the beams if you ask why did you only build a 4 kilometer long detector, why didn't you make it 20 kilometers, 30, 40, pick your number. It's because of the vacuum system, it's very expensive. You are not just taking a laser beam and shooting it through space, it's going through, through a forest. It's going through a vacuum tube, and that's where the expense lies.
Okay, over here.
Have you gained insights into time? Like we've gained insights into space and gravity through space. Has there been other things that you can?
Yeah, so as soon as you talk about relativity, you can't really separate the two. If you notice, I never really say space. I always say space-time. And if you look at those animations or movies that I've shown of Einstein's equations, in every one of those simulations, space-time goes together. So it's included in there. And in the way that it was shown in the movie, for example, was when you saw the bumps form on the surface of the two black holes, that's the spatial part, if you will. And the color coding was the passage of time, which is that as you get, what happens is, it's very bizarre, but as you get closer and closer to a black hole, your clock starts ticking more slowly relative to someone far away. And so, time slows down, and that was depicted by the color coding. So it's all, you can't solve space and time separately, and you shouldn't.
I think we're over there now.
Oh, so the amplitude was 10 to the negative 21st, right? So does that have anything to, I don't know how to phrase this better. So if two objects are massive enough to interact and to cause these space-time gravitational waves, does their mass impact the strength of the gravitational waves at all?
Very much so. So the amplitude of the gravitational wave, in very rough terms, depends on the masses of the objects and their distance. And that's why the signals from the black holes are so much stronger if they were at the same distance than the signals from the neutron stars, because the black holes are 10 times heavier.
So I'm going to do two more. I have one in the back.
Thank you very much for your talk. You mentioned earlier on that a certain amount of energy from the collision of these massive objects gets converted into the gravitational wave. Does that energy remain as a gravitational wave forever, or does it ever get converted into another form?
Yeah, so that's a good question. So the gravitational wave is attenuating as it passes through space, and in part it's attenuating in the same way that a light wave would, because it's spreading out. So it's spreading out the energy over larger. So it's falling off as 1 over the distance from the source. But yeah, a different way to ask the question is, as this gravitational wave passes through our detector, does it deposit any energy in there? And you can calculate that it does, and it's actually a very, very small amount. And that's why it basically passes through everything without losing much information.
Okay. And our last question here.
Okay, so I was wondering, can you use this gravitational wave technique to study more about dark matter?
Yeah, that's a really good question, and you're right to wonder. It turns out, unfortunately, no, and the reason for that is at least the dark matter that we've seen in the universe so far is very diffuse. And so, and we don't have the capability or the sensitivity to see something so diffuse. Remember, I told you have to be compact, right? And you have to have objects that are sort of on the scale of a Schwarzschild radius or a scale of a black hole. For this class of objects that we're looking at these sensitivities, the dark matter is too diffuse. Now, if you had dark matter that clusters into clumps, as we think it happened sometime in the formation history of the universe, maybe. But these are completely speculative sources. There's nothing no evidence for it.
Okay. Well, before I ask you to thank Professor Mavalvala again, you might have seen little cards on your chairs. If you fill them out, you can just leave them on your chairs and they'll be picked up. So with that, let's thank Professor again.